All right, welcome back to 5.2, and what we're going to work through is an extension of what we did yesterday. So we're still going to be analyzing factored form. We're going to see how it applies to a graph. We're going to be writing polynomials from its function, and today we're actually going to do a practical application of all this. So by way of review, note that this negative here applies to that down there, so I'm going to move it there. And we want to write a cubic polynomial with these zeros. So remember, a cubic polynomial, and it should actually say function in there. All right, so one theorem slash property slash whatever we learned yesterday was that whatever the zeros are, it's that, but opposite, to find the function, or excuse me, to find the factors. So x plus 4 is the factor related to this 0. How about this one? Well, this one's x minus 4. X minus 6. It's the opposite of what you see. Oh, but Swenson, look, I see a positive 4 and I wrote a positive 4. No, no, no. The red one's negative here, so it's positive there. The blue one's positive, so it's negative there. So that's what we do. Now, we do want to write this in standard form, so I have to multiply out accordingly. This first one, many of you may notice that this is actually conjugates. So the first part jumps straight to x squared minus 16. Whenever you have a product of conjugates, you take the square, you minus, and you take the square. Now I'm going to bring down the x minus 6. So after we do our double distribution here, we end up getting this. One mistake. What mistake did I make? Oh, I forgot the square right there. It's already coincidentally in standard form, so I don't have to rearrange my terms. And it's also, there's nothing to combine. Often we have like terms, but because this one's squared and this one's to the power of 1, it's a linear term, they don't combine any further. Next up, we want to factor each polynomial. So, what is something that we can pull out of both of these? Anybody? Anybody? Yay, so we see that I can pull out an x. When I do that, this becomes x squared minus 81. And what do we notice about this right here? It's a difference of 2 squares. If you forgot that and you say, I don't get the difference of 2 squares, that's fine. Factor it. So I put negative 81 in the numerator, in the top, x is on the wings here, and 0 on the bottom. What? Because there is no b term. 0 goes there. So what two numbers multiplied in negative 81 but add to 0? Negative 9 and positive 9. Had you known that this was a difference of 2 squares, you could have just jumped to the conjugates. X minus 9 times x plus 9. And there's factored form. Yes? And b here, we're going to pull out an x. So now I get x squared plus 9x plus 18. And if you don't see the quick factors there, let's put 18 on top, 9 on the bottom, x is on the wings, 6 and 3. 6 times 3 is 18. 6 plus 3 is 9. So I bring down the x plus 6, and the x plus 3. Box or circle to show my commitment to it. So earlier you had asked about multiplicity, what multiplicity means, and here is multiplicity. Multiplicity is the number of times a factor appears, and remember, when we say factor, it also means it's the number of times the 0 shows up as well. Now, I'm not saying the number 0. I'm saying how many times a 0 shows up. So factor in this case might be easier to say. Appears in factored form of a polynomial function. All right, so take, for example, this. If we were to prime factorization, do the prime factorization of 30, notice I can do 5 and 6 here, and then 2 and 3. So when we break up 30 into prime factorization, I get 2 times 3 times 5. So what we notice about each one of the factors is that they show up only once. The 2 shows up once, 3 shows up once, 5 shows up once. Well, that's not always the case. Notice with 24. 24, I'm going to split up. So I get 4 and 6, 2, 2, and 2 and 3. And so if I do prime factorization of 24, I get 2 to the third power times 3. 1, 2, third power. So if we're talking about how many times the 2 shows up as a factor, the answer here is it shows up with a multiplicity of 3. That's how many times the factor shows up, 3 times. So the 3 has a multiplicity of 1, and the 2 has a multiplicity of 3. That's exactly the same thing here. All we're doing it is looking at factors that happen to be more complicated looking. So let's take a gander here. So if we're going to find the zeros, just to show you what happens, you do not have to always show this work, especially since most of it is completely mentalable, is notice that this now splits up using the zero product property. It splits up into 3 different equations. X is 0. One of the x minus 8's is 0, and the other x minus 8 is 0. Now notice the redundancy there. I don't need to write that x minus 8 twice because no matter what, I'm still going to get the answer to be x is 8. So in talking about multiplicity, we see how many times things show up. 0 shows up once. So it has a multiplicity of 1. So the number 0 is also a 0. It's a 0 of the function. And it has a multiplicity of 1 because it only shows up once. We'll look at the behavior in just a moment when we look at the graph. Next, 8 is another 0, shows up twice, so it has a multiplicity of 2. Now, here's the key thing. What we want to do is look at this 0 right there, which is the number 0, and this 0 here, which is the number 8. What does the graph look like at that particular point? So notice this. If I were just to focus in this small section there, what does that green look like to you? And what about this one? What would this small section look like? What familiar shape does that look like? Well, the green essentially looks like a line. So the behavior of the graph at that particular point, at this 0, it looks like a line. Now, it's not perfectly aligned because notice up here it starts to curve, and then it has a turning point there. And somewhere along the line here, this starts to look like a parabola, which is the behavior of x to the square function. This linear is the behavior of an x function. In other words, the multiplicity tells you what the behavior of the graph will look like here. What? The multiplicity tells me what the graph is going to look like at this particular 0. This has a 0, a multiplicity of 1. Because of that, it's going to look linear when it passes through the number 0. This has a multiplicity of 2, so as it passes through 8, it's going to look like a parabola. So, here is the key concept. This exactly says that to what we just repeated. Let's read through this. If A is a 0, and it has a multiplicity of n in the polynomial function y equals p of x, then the behavior of the graph at the x-intercept A will be close to linear, very close to linear, if the multiplicity is 1. If the multiplicity is 2, it's going to look quadratic, like a polynomial, etc. If we have a multiplicity of 3, it's going to look cubic. So if I had x cubed as a factor, which means that x would be 0 and it would happen 3 times, which means at the graph, it would look like this. Notice it looks kind of quadratic. It looks kind of, cubic. So each one of these tells me what it's going to look like just in the micro setting just in this location and this location, what the graph looks like. This one. Here, we want to find the zeros of this function, and we also want to state multiplicity of things. So to find the zeros of them, I'm going to start by writing it in this manner with the 0. Now, some of you notice that we have an x squared that can come out. And now I end up with x squared minus 8x plus 16. And if you need to see the snowflake here, we have 16, negative 8, so negative 4 and negative 4. So here, x squared and x minus 4 twice, so that's a square. So what are my zeros? Well, my zeros are 0, which has a multiplicity of 2. And then the other 0 is positive 4 that also has a multiplicity of 2. So because both of these have multiplicities of 2, they're both going to look parabolic at their particular point. So let's see over here. At 0, right here, at 0, look, it looks quadratic, parabolic. Next, at 4, this one looks parabolic. It won't necessarily be exactly the same. These ones coincidentally look very close to being just copies of each other. But notice it looks parabolic there.